So in this video, I want to introduce this idea of an ensemble model, and particularly I want to introduce this one that we call random forest, which is particularly an example of bagging. I'll explain what all those terms mean. So again, right now in this kind of ML pipeline, we're really going to be thinking about using a different ML model. So the type of model we'll be considering, what we call an ensemble model or a model ensemble, is instead of learning a brand new type of model that's more powerful than trees, say something like deep learning or neural networks, what if instead we try to turn the tree itself into a more powerful model? So what if we can combine a bunch of not very good models in such a way to make a better model overall? And this idea of combining models we call a model ensemble, a combination of these models. So a model ensemble is a collection of generally weaker models that are combined in such a way to create more powerful ones. This doesn't necessarily have to be combining weak models. You can combine really good models. In fact, a lot of the state-of-the-art systems use really good models that people trained individually and then combine their results together. And generally, most ensembles follow one or of two kind of approaches for how they can do this combination. One is called bagging or bootstrap aggregation, and the other one's called boosting. And today we're going to talk about two such examples of these kind of types of ensembles. Random forest was what we're going to introduce in this video, and then in class we'll introduce the AdaBoost algorithm as an example of boosting. So I'll explain what bagging and boosting mean, but I'm just going to give you an overview of kind of what we're talking about today. So here's an overview of what a random forest is. For this kind of ensemble. A random forest is a collection of T decision trees. Each decision tree is going to cast its own vote for what it thinks the ensemble should predict, and then the ensemble will just predict the majority vote. So the big idea is instead of just training one decision tree, we're going to train a bunch of decision trees and have each one have an equal vote in what the result should be. It's a democratic way of modeling. It says instead of trying to come up with one really good model, just come up with a bunch of models and have each one vote. And hopefully, the idea being if you average over a lot of models, then maybe you might get better predictions overall. So if you have three decision trees, one saying that the class should be X, the other saying the class should be Y, another saying the class should be X, each individual model gets its own vote, and the ensemble combines them with something like majority vote. So in this example with just three, it would output class X. Now, how do you go about training these trees? Because it might not be clear if you just train a decision tree on your data and then train another decision tree on your data, you'd get the same tree. Importantly, in terms of this ensemble, you want your models to be different. If they're all the same model, it won't quite work. So the way to do this, or the way that we're going to get this in random forests, is random sampling. If I just have one data set, I couldn't learn more than one tree. So instead, we're going to create many kind of perturbations or change versions of our data set. And specifically, we'll use this technique called bootstrapping. We're going to bootstrap our data set. The idea is create many similar datasets that aren't exactly the same, but very similar by random sampling with replacement. What I mean by that is suppose our original dataset had 3 rows. Observation 1 with x 4.3, y 2.4, observation 2 with x 2.1 and y 1.1, observation 3 with x 5.3 and y 2.8. What we'll do, a bootstrapped version of this dataset, is one that has the same number of rows, but the rows are sampled randomly with replacement. And we do this many, many times to get many versions of our data set. So in this version, you might have 3 represented twice and 1 represented once and 2 represented no times. Sometimes you might have all 3 represented, but other times you won't. And this randomness in which data you choose will then affect, when you train a tree on that data set, which tree is learned, because it's getting a slightly different data set each time. Do note that many implementations of random forest also randomly sample which features to use. So not only do they randomly sample which rows, but they also randomly sample which columns you select as well. And this is just to add more randomness to the system so that each tree learned is more different than the others. That's it. That's the big idea. This idea of bootstrapping is just make many, many data sets derived from your original one that are derived by random sampling. And importantly, you have to randomly sample with replacement. That with replacement is really important because if you were to do 3 draws from a data set with 3 rows without replacement, you would get the same data set each time. So that with replacement makes it possible so that some data points get overrepresented in some data sets and other data points get underrepresented in other data sets. And that overrepresentation and underrepresentation across different data sets will hopefully average out to a better ensemble overall. So here are the details of how random forests work. Random forest is a type of ensemble model. Remember, when I say ensemble model, I mean it's a model that uses many submodels as part of its prediction. And in particular, it's using a technique that we call bagging, or bootstrapped aggregation. It's called bootstrapped because we're using this process of bootstrapping to generate many versions of our data set. And aggregation because we're going to take the results of all of these individual bootstrapped models and aggregate them into one answer. So it's an ensemble that uses bootstrapping aggregation. When we train the trees, we're going to train one tree on each bootstrap data set. And particularly, we're going to let those trees overfit. We're going to make each tree learned on each data set grow as tall as it wants. We're not going to worry about cross-validation and choosing the right height. We're just going to let each individual tree overfit. This might sound terrible at first. You're like, whoa, Hunter. I thought overfitting was bad. Why would I let these models overfit? But recall, because we're averaging out over the ensemble, overfitting actually might not be too much of a problem. What bagging is trying to do is take advantage of what it means to have a high variance model. Remember, a high variance model is one that might overfit and varies significantly on slightly different versions of the data set. But remember, high variance models tend to have low bias. Remember, when you average out over all of these high variance versions you could get, it ends up being close to the true function. And this is the key idea to why bagging works, is the ensemble you create has a bunch of really overfit models individually. But when you average out over all of them, you hopefully get something close to the true function because high variance models tend to have low bias. And we're kind of trying to learn this average function by averaging over many high variance models. And this is exactly what we're trying to do here. If we average over a bunch of overfit trees, we get an ensemble that should have low bias. And because the results are averaged over many high variance models, we'll hopefully have low variance as well. And so generally, these models only get better as you add more and more trees to the ensemble. As you keep adding more trees, you could tend to decrease the variance more and more. And just by using bagging in the first place, you've decreased bias. Now, it's a little bit more complicated how this story of bias and variance relate here. There's always going to be some bias with the random forest, and you're never going to be able to decrease that bias further by adding more and more trees. The hope is essentially that by averaging in the first place, we're already at a lower bias. And by averaging over more trees, we decrease we decrease variance further. But you generally won't be able to decrease bias anymore because the decision tree is one type of model, which might be different than the true function. Okay. So here's the random forest algorithm. Make T random samples of the training data that are the same size as the training set, but sampled with replacement. And then for each one of those data sets, train a really large tree. Let it overfit. When it's time to make a prediction for a new data point, for a given example, ask each tree in the ensemble to make a prediction for what it thinks the result should be. And then take a majority vote. Find the class that has the highest count and predict that. If there's a tie, you have to have some tie-breaking scheme. But that, again, shouldn't really matter too much. Now, this type of model is used all over the place. It is a very good model to start with, and it can be very powerful. In particular, one of the most one of the most famous examples of random forests is Microsoft actually used it in their Kinect system, the little camera thing that they came out with an Xbox, I don't know what, in like 2010 or something like that estimates like what pose you're in. A pose is like trying to estimate where your arms and your legs are in proportion to your body. They used a random forest model to get this pose estimation, which is a really important task in something like a Kinect system, and it has been very influential in a lot of similar tasks. Now, why do people use random forest is, well, we're essentially taking advantage of overfitting by averaging out over many models. It turns out that these many overfit models can average out to a strong ensemble overall. And this technique is very versatile. It works really well in a lot of cases and can have several different purposes for why you want to use this. You can use it in classification or regression. You can also use it in things like clustering that we'll talk about next time. And importantly, these kind of having many models can actually serve as a really great way for trying to understand feature importance. That this kind of averaging over many data sets can help you understand whether one feature was very useful in a lot of these random samples. And this gives you just a little bit more confidence in some cases about how feature importance works. And it turns out random forests just work. They tend to have a lot less hyperparameter tuning. It's a good out-of-the-box model. What I mean by that is you can really just load it in and just train it, and it generally gets decent accuracy in a lot of context. In this case, more trees is almost always better. If you add more and more trees, you're going to get a better and better result. Now, it might take longer to train because you have to train each tree, but generally you're not going to overfit by adding more trees when you're considering random forests. Now, they do have other hyperparameters, and you definitely should do hyperparameter tuning, but you get a little less bang for your buck in terms of other models where hyperparameters are very, very important. These models, or in terms of random forests, have really, really good, or maybe I should say really, really decent default performance. So if you're ever trying to come up with a baseline for something, like you want to solve a problem, I always recommend, well, try something. If it's a classification problem, try something simple like logistic regression, and then maybe also try a random forest. And these can give you really good baselines that if you want to try something much fancier, you can compare against. Also, one reason random forests are generally very popular in the realm of big data is that you can train them in parallel. What I mean by that is that if you want to train 1,000 trees, you can actually just send data to 1,000 computers and have each one train its own tree independently, which is a very nice kind of break up in responsibility compared to most models where there's a lot of sequential decision making, which makes this parallelization really hard. And so when we're talking about massive scales of data, these random forests work really well. It's one of these types of models that we call embarrassingly parallelizable, that you can really just, we're not going to teach you in this class how to write parallelized code. That's a very complex thing, but it's one thing that's very easy to do if you know how to write parallelized code, because there's so much kind of disjoint ownership over each part of the training that you could really just give each computer its own tree and everything's happy. And a lot of other models we'll talk about really make that quite difficult. And so I guess I had a brain break from the last time, but that's all we're going to talk about for today. In the class today, we're going to talk about a different ensemble model called AdaBoost that tries to take a very different approach than the random forest, but it's still going to be an ensemble combining many small models. And we'll talk about kind of how it differs and what properties it has.